The first part of this problem for finding our potential function, we're asked to determine whether the vector field is conservative on this specified region, R3. So first of all, what I'll do is I'm going to try and set up how to remember the partial derivatives that I need to compare. With the first function, we use the other variables. Second, we use x, z, and h, x, y. So there's going to be 3 different comparisons we need to do here to remember which ones to compare. 1, 1, 2, 2, 3, 3. So first we have number 1, we have df dy. Okay, evaluating f, the partial derivative with respect to y is equal to 1. Okay, and then over here we have g and the partial derivative with respect to x. dg dx. And when we take this partial derivative with respect to x is equal to 1. Okay, so the first one checks out. Second, we have df dz. And z, partial derivative, is equal to 1. And then we also have for 2 dh dx. And that one also, take the partial derivative, that's also equal to 1. So that one checks out. And then our third one, we have partial derivative dg dz. And that is also 1. And finally, 3, we have dh dy. And as we can see, that also is 1. So, since this checks out as conservative, our next step is to then determine the potential function. And of course, to determine a potential function, it takes a lot of integration and derivatives. So, in defining each part, we know that this is going to be phi x. We'll go ahead and call this f. We have to equate phi y equal to this as g, phi z equal to h. So first of all, our first step, in looking at this, the definition of it, this is the partial derivative of phi dx, and that's equal to y plus z. So our first step in solving for potential, we need to integrate y plus z, and this is going to be dx. So we integrate this, we get xy plus xz plus some constant that we'll call cyz. So this is our constant, which is going to be serving as a function of y and z. Now to figure that out, our next step is now, well, we just integrated, we have to do a derivative. So we'll go ahead and take a derivative of this that we just calculated. And this is, we're calculating the derivative with respect to y. So when we do that, well, we have, with respect to y, we have x, and then now we're going to have plus our constant y of yz. Okay, now in order to figure out what this cyYZ is anyway, we can at least come up here and we're going to compare it to our g. And we compare the two. we say g is equal to x plus z. Okay, since our phi y is equal to g, we have the x, then we can conclude from this that at least part of this, the cy yz, is equal to z. So our step 3 now is going to be integrating. Of course, we just did a derivative. It's time to integrate. So we do an integration this time with respect to y in order to calculate for c y z. And that's going to be equal to our z dy to solve for that, which, simple enough, that's going to be yz plus, we have another constant that we're bringing along. We'll go ahead and call this dz. So let's bring down now what we've got so far for our phi. Phi equals xy plus xz plus, now we've just solved for that down here, yz plus our final constant that we need to solve for in step 4. And in order to do that, we are going to calculate, differentiate the equation that we just did with respect to z. So when we do that, with respect to z, well, that's going to give us, that drops off. We've got x plus y plus then the constant, which now is going to be d prime of z. Okay, so now we compare this, it's the z up here with the h. Remember the h then was equal to just x plus y. Well, since these two are supposed to be equal, the only way this is going to be working is if the d prime of z is equal to 0. And in that case, we're left with our final equation, phi equals xy plus xz plus yz. Since now the integral of this is 0, it would just be a constant that has no variable in it. So this gives us our final equation for the potential function.